Hello, this is Mrs. Sharp. These are notes for 3.4, and in 3.4 we're going to talk about some average atomic mass and how that is related to the mass number of an atom. So first we're going to explain how those two numbers are different, and we're going to describe how each one is found. Part of this is explaining why the masses you find on your periodic table are actually decimals instead of whole numbers. We have actually talked a little bit about that being an average. Today we're going to talk about how that average is calculated. So our first question in our notes is, what is average atomic mass, and also how is it calculated? So let's define average atomic mass. This is the weighted average value of all the isotopes in a natural sample of an element. So there's a couple things there that are bolded and written in capital letters, so let's talk about that. First is the weighted average. So let's discuss what that means really quickly. So the weighted average of something means that certain parts of it factor in more importantly than others. For example, your grade in this class is a weighted average of a few things. So first you have LTAs, which are weighted at 70%. And then you also have labs, which are weighted at 10%. Then you have homework, classwork, or formative assessments, which are worth 1%. You have unit tests or midterms that are worth 19%. So altogether, that represents your entire grade. However, you can see that your grade and LTAs factor in much more heavily. So in other words, they're the most important factor in your grade, whereas homework formative assessments are the least important. That's called a weighted average. So your grades are averaged, but they're averaged in such a way that the LTAs are more important. So with average atomic mass, the same kind of thing happens, but we take, instead of, like grades where LTAs would be the most important, it's reflected by how many of the atoms have a certain mass. The other part of this is a natural sample. So a natural sample means that no man-made isotopes are included. And a lot of isotopes are man-made. So that leaves out quite a lot of the other isotopes of elements. So it's just the natural isotopes, ones that you could find without having to make them in a lab. So let's continue on here. Each isotope of an element has a natural relative abundance, or a percent abundance. Now this is something that you're going to have to be given. So the natural relative abundance, or the percent abundance, is going to be given to you, and that's simply what percent of the element is which isotope. So in other words, which isotope is most common, which one is maybe not as common, but what is the breakdown of those different isotopes? There's a really cool website that I found, and it's just www.ptable.com/#, isotope. And I will also post this up on the blog, but it's really cool if you have some time to play with. What this shows is all the elements on the periodic table, and if you click on one of the elements, so I'll go ahead and click on lithium, it shows the isotopes for lithium, and then if you look right here and you go and click or poke or go over the different isotopes, it will actually show you right here, about fourth down, the abundance of each isotope. So for lithium, if I were to put my cursor on lithium 6, you can see that the percent abundance is 7.59. So right there, 7.59%. So of all the lithium that's naturally occurring, that's not man-made, of all the lithium atoms, 7.59% of those have a mass of 6. So see, that's lithium 6 right up here. But then if I move my cursor over lithium-7, you can see that that changes, lithium-7, and the remaining amounts of lithium, 92.41%, is lithium-7. So that's what it means when it's a weighted average. So since most of lithium has a mass of 7, that's going to factor in greater than the lithium that has a mass of 6 because there's not as much of it. So I just wanted to show you some other ones of these because it's kind of cool. So get on and play with it. Carbon. I'm going to click on carbon. So these are the isotopes of carbon, carbon-12, carbon-13, and carbon-14. So you can see carbon-12 is really most of it, 98.93%. And then carbon-13, 1.07%. And carbon-14, 0%. Or, pretty much nothing. So not really naturally occurring, not factoring in at all. So those are your percent or relative natural abundances. So this would be a really handy tool for if you were to have to calculate the average atomic mass. So if you were asked to calculate the average atomic mass for any of those elements, you would have to just go through 3 steps. The first is that you're going to multiply the atomic mass of each isotope by its percent abundance, but you have to do it as a decimal. So remember, a percentage expressed as a decimal, you just divide by 100. So you're going to multiply the atomic mass by its percent abundance. You have to do that for each isotope, and I guess I should add in there each natural isotope. And remember, on that periodic table, if it's not naturally, the percent natural abundance would be 0%. So after you do that for each isotope, you are going to simply add up those results. So all of the isotopes that you did in one, you're going to add those up together, and then just check the periodic table to see if it's reasonable. So it might not be exactly what your periodic table says, but it should be really, really close. So those are your steps. So we're going to try a practice problem here together. And here is the example. It says naturally occurring boron consists of 19.78% boron-10, which has a mass of 10.013 AMU, and 80.22% boron-11, which has a mass of 11.009 AMU. Calculate the average atomic mass for boron. So we're going to go through those steps that you just saw right here. Multiply the atomic mass of each isotope by its percent abundance. Okay, so here we have 2 isotopes, and I'm going to highlight those. Isotope 1 is boron-10, which is 19.78% with a mass of 10.013 AMU. And isotope number 2, I'm going to use green. Isotope number 2 is boron-11, which is 80.22% of all the boron, and its mass is just over 11 AMU. So those are my 2 isotopes. So I'm going to go ahead and do my green first. So boron-11. So boron-11, we're going to take its percent abundance in decimal form. So that is 80.22, but divided by 100, it will be 0.8022. And we're going to multiply that by its mass, which is 11.009 AMU. And when I put that into my calculator, 0.8022 times 11.009, I get, and here's the thing, we got to use sig figs. So we're going to have 4 sig figs since 0.8022 has 4 and 11.009 has 5. So when we do our sig figs there, we're going to get 8.896 AMU. Okay, and then we're going to do the same thing for our second isotope. So we're going to take our 19.78% becomes divided by 100, 0.1978, and we're going to multiply that by the mass, which is 10.013 AMU. And I kind of messed up my parentheses there, I guess. I don't have enough. There we go. So 0.1978 times 10.013 gives me, again, 4 sig figs here, 1.981 AMU. Okay, so look at this. Because of the fact that it's a weighted average, we are going to reflect a lot more of this particular isotope because it's a lot more abundant than the second one here. So the next step is to add our totals up. So we're going to add these two numbers together. And if I add up 1.981 and 8.896, I get a grand total of 10.877 AMU. And remember, if you're adding and subtracting, you don't count sig figs, you count decimal places. So my answer should have the number of decimal places as my least decimal places. They both have 3, so my answer can have 3. So I'm going to check my periodic table, and for boron, yeah, that's really, really close. So that is my weighted average. That's where that number comes from. So this is kind of interesting because if you just have boron 10 and boron 11, and there's a lot more boron 11, the average should be closer to 11 than 10 because there's more of it. So 10.877 reflects that there's more boron 11. If there's an equal amount of boron 10 and boron 11, the average would just be 10.5. But since there's more boron 11, it factors in more heavily, and that's why our average is actually closer to 11. So what I would like for you to do now is to try this. This is the isotopes of zirconium. So what you have here are the 5 different isotopes, the percent relative abundance or the natural abundance, and the mass of each isotope. So what I would like for you to do is to use this data to calculate the average atomic mass. And if you have Mrs. Sharp, when you return, we will go over that problem and see how you did. So have a great day and talk to you soon.